Okay, here we go. So Matt just gave a very nice talk on parcellation approaches using multiple modalities. So as most studies only have the resting state functional M data, therefore in my talk I will mainly focus on the parcellation approaches using resting state functional MI. The brain is active even at rest. So this video from Daniel shows the functional MR signal recorded when the subject is lying at rest in the scanner. As we can see, these large spontaneous activity fluctuations appear throughout the brain. So these intrinsic fluctuations are relevant here is because, as demonstrated by Biswa, these fluctuations can be used to measure the connectivity in the human brain. So for example, if we put a seed in the posterior cingulate cortex, and the time course of PCC is shown as a blue line. And if we compare the time course of PCC with the time course of region A at angular gyrus, shown in red, we can see that the time courses are very similar with the Pearson correlation around 0.2. On the other hand, if we put a seed at region B and compare the time course of PCC with the time course of region B shown in brown, we can see that this time the Pearson correlation is only around 0.1, so they are less likely to be correlated. So this correlation between the functional MI time courses is called resting state functional connectivity. So this approach of taking a seed and correlating the time course of this seed with the entire brain is called the seed-based functional connectivity. If you let the seed move around the brain, we can see that the functional connectivity patterns changes a lot, suggesting that adjacent locations can have very different functional connectivity patterns. So this has motivated a lot of studies to extract the brain networks and parcellations using functional connectivity. So in this talk, I will first describe several approaches for estimating the network level parcellation using functional connectivity, and then I will talk about the area level parcellations. After that, I will introduce the individual specific parcellation approaches, and finally, I will describe methods to assess the parcellation quality. So let's start with the network level parcellation. So the resting state functional connectivity is a very promising tool for identifying large-scale brain networks. So the brain regions can be grouped into around 10 to 20 brain networks, each associated with various cognitive functions. So the brain regions within each network normally share similar time courses or connectivity patterns. So here I'm showing you a few examples of the network level parcellations estimated by different approaches. So these network level parcellations can be grouped into two categories. The first category is hard parcellation. So for hard parcellation, each vertex can only be assigned into one network. Mixture model is one of the common approach people can apply to estimate a hard network level parcellations. So for example, here I'm showing the 7 network parcellation from Yo 2011. So different color represents different networks, and we can see that the networks are not overlapping with each other because each vertex is only allowed to be assigned into one network. So the mixture model is trying to group the brain regions with similar functional connectivity patterns together. For example, in this case, the posterior cingulate cortex and the medial prefrontal cortex have very similar functional connectivity patterns. Therefore, they are both assigned to the default network. However, for this region, even though it's spatially close to the PCC, but the functional connectivity pattern is very different. Therefore, it's assigned to a different network. Another approach to estimate the hard network level parcellation is using graph theory. So in the graph theory-based approaches, the functional connectivity is constructed as a graph. So the graph node indicates the brain region. And the graph edge represents the functional connective strength between two brain regions. So in this plot, the thicker edges represent the stronger functional connective strength between two brain regions. By applying some community detection approach, such as the info map or the spectral clustering, and we can get we can group the graph nodes into different networks. So in this plot, the different color represents different networks. Now let's talk about the soft network level parcellation. So in the soft network level parcellation, each vertex can be involved into multiple networks. So spatial ICA is one of the most popular approach that people can use to estimate the soft network level parcellations. In spatial ICA, the resting state functional metadata can be seen as a decomposition of a set of spatially independent maps and their corresponding time courses. So here I'm showing the default network, the spatial map corresponding to the default network from Smith 2009. And if you compare it with the default network estimated by a hard network level parcellation, we can see that actually they look very similar. Another approach to estimate soft network level parcellation is fuzzy C-means. So the idea is very similar to the mixture model. So it tries to group the brain regions with similar functional connected patterns together, but the fuzzy C-means allows for weighted alignment of each vertex to more than one network. So in this example, the yellow color indicates the brain regions have a higher probability to be assigned into the default network, while the red color indicates the lower probability for this. Again, if you compare it with the default network from the hard network level parcellations, for example, here I'm showing the Yo 2011 and the Power 2011, and we can see that the structure of the default network are actually very similar. So this is good because it suggests that the large-scale networks are consistent across studies and methodologies. So here I'm going to list several publicly available network level parcellations here. So you can either download the parcellation, I cannot see it now, anyway. So you can either download parcellations or you can download code and apply the code on your own data to generate your own your own group level network level parcellations. So I will now move to the area level parcellation. So I have just shown you the network level parcellation. So these are a few examples of the network level parcellation approaches, including both soft and hard parcellation. However, as we know from the systems neuroscience, that the cerebral cortex is roughly composed of 300 to 400 cortical areas. Therefore, each of these large-scale networks likely contains multiple cortical areas. Each area has its own distinct function, architectonics, connectivity, and topography. So here I'm showing you another three examples of the area-level parcellations, and we can see that each of the large-scale networks in the network level can actually contain multiple cortical areas in the area-level parcellation. So again, we can also group the area level parcellation into hard and soft parcellations. So for the hard area level parcellation, each vertex can only be assigned to one parcel. So we can apply the clustering techniques such as the mixture models and clustering technique and spectral clustering to estimate the hard area level parcellation. So the clustering techniques try to group the regions with similar time courses or connectivity patterns together. However, as I mentioned in the previous slides, that the two spatially far apart regions, for example, the posterior cingulate cortex and the medial prefrontal cortex, they can have very similar connectivity patterns. So if we group these two regions into one parcel, then this parcel will be spatially distributed. Therefore, most of the time we have to add additional constraints into our model to ensure this spatial contiguity. So here I'm showing you 3 examples of the hard area level parcellations. In this, the mouse is gone. So for example, in the shaver parcellation, you have to add additional constraint, like we have to say the vertices have similar x, y, z coordinates are more likely to be grouped into the same parcel to ensure the spatial contiguity. Okay, so another way to estimate hard area level parcellation is called the gradient-based approach. So this is a method pioneered by Steve Peterson's group. So this approach is based on the idea that the connectivity patterns can abruptly change from one location to a nearby location. For example, these 2 brain regions have very these 2 nearby regions have very similar functional connectivity patterns, while these nearby regions have very distinct functional connectivity patterns. If we map the local changes of the functional connectivity across the cortex, we can get the gradient map like this. So the red color indicates rapid change of the functional connectivity across at this location, and the dark color indicates slow change of functional connectivity at this location. By applying some post-processing, for example, the watershed algorithms, then we can convert this gradient map into the Gordon 2016 parcellation shown here. So these are the area level parcellations. We also have the soft area level parcellation. So in this case, each vertex can be assigned to multiple parcels. Again, the most common way to achieve this is by performing spatial ICA with higher dimensionality. So in this example, I'm showing the 4 spatial maps corresponding to the default network by performing spatial ICA with 300 dimensions. So here again, I'm listing all the publicly available area level parcellations I can find. So you can also download parcellations or applying the code to generate your own area level parcellations. So far, I have described approaches for estimating network level and area level parcellations. I will now move to the individual specific parcellation. So I've described approaches for estimating the network level parcellation, as well as the area level parcellation. So these parcellations are normally generated by averaging data or concatenating data across many individuals. If you compare it with the individual specific parcellations, we can see that the group level parcellation do not capture the individual specific features. However, these features are real, and we believe they're real is because we can use these features for behavior prediction. So this figure shows the individual specific network level parcellations of 3 representative subjects. So each column represents 1 subject. The first row is day 1, and the second row is day 2. So the parcellations are generated by using functional ML data from day 1 and day 2 separately. So we can see that there are fine-grained network details that are actually highly replicable across sessions. So this figure shows the individual specific area level parcellations of 3 subjects from Lee 2019. So each row corresponds to 1 subject. The first column is the test sessions. The second column is the retest sessions. So we can see that the individual specific features in the area level parcellations are also replicable across sessions. As studies have shown that the network topography vary across subjects. Therefore, so we are thinking that maybe this can be used for behavior prediction. And indeed, this plot shows the prediction accuracy of certain cognitive measures using the network topography, and we can see that it can achieve the prediction accuracy around 0.13. The red line shows the prediction accuracy from HTTP MAC control, which uses the functional connectivity strength for behavior prediction. And we can see that using network topography is not worse than using functional connectivity strength for behavior prediction. So we just see that the network topography can be used for behavior prediction. And there are a lot of studies that have demonstrated that the functional connectivity strength can be served as a fingerprint of human behavior. So this plot shows the using the functional connectivity derived from the group level parcellation. The fluid intelligence can be predicted with around accuracy 0.2. So this prediction accuracy can be further improved if we use the individual specific area level parcellation to estimate the functional connectivity for behavior prediction. So here I'm listing the several individual specific parcellation approaches that can be used to generate individual specific parcellations. Of course, there are more. Actually, there are within our group we are also trying to get because in here I'm mixed up with the network level and area level parcellation approaches. Because currently the plot biology one is the one that are currently available for downloading. But it's worth to noting that a lot of the group level parcellation approaches can also be applied on the individual data to estimate individual specific parcellations. So in the last part of my talk, I will describe how to assess the parcellation quality. So we just shown that using network topography or functional connectivity, we can use it for behavior prediction. So we assume that a better parcellation quality should indicate higher prediction accuracy. So we can then use the behavior prediction as an indicator of the parcellation quality. Recall that the cortical areas have traditionally been defined based on function, architectonics, connectivity, and topography. Therefore, we can also use these criteria to assess the parcellation quality. To evaluate the function, we can use the task functional MRI. So this figure shows the task contrast maps and corresponding resting state networks from two MNC subjects together with the group average contrast map. The blue color indicates the task elevation in response to the hand movements. And we can see that it corresponds very well to the orange hand smart motor network. The yellow color indicates the task elevation in response to the tongue movements. So we can see that it corresponds very well to the blue face smart motor network boundaries. So the shape and the size of the task activation patterns varies across subjects. Therefore, we would expect if we overlay the parcellation boundaries on the task activation patterns, we would want to see that the task activation strength to be uniform within the parcel or network. To measure these things, so there is a metric called fraction overlap. So to compute the fraction overlap, we first threshold the task activation map at the threshold level, and then we can compute the fraction of the task activated vertices that fell within the parcels as opposite to the boundaries between parcels. So the higher value indicates better parcellation quality. However, this metric is very sensitive to the threshold level. Therefore, normally users have to perform the fraction overlap with different thresholds. To avoid thresholding, there is another way to compute to evaluate the function. It's called task inhomogeneity. So the task inhomogeneity is defined as a standard deviation of task activation within each parcel or network. So lower task inhomogeneity means that the task activation strength within a parcel is more uniform. So this plot shows the task inhomogeneity of individual specific network level parcellations from the 10 MNC subjects. So the red dots represents the inhomogeneity of individual specific parcellation. The blue dots represents the inhomogeneity of the group level parcellation, and the black dots represents the inhomogeneity of other subject parcellation. So we can see that the individual specific parcellation has the lowest task inhomogeneity, means that the individual specific parcellation has the best parcellation quality. So to evaluate the architectonics, we can look at the histological alignment. So here we can see that the Gordon parcellation and the Schaefer parcellation aligns very well with the early sensory and late motor areas. Therefore, we can overlay the parcellation boundaries on top of the architectonic boundaries to evaluate how well they can align with the architectonic boundaries. To quantify these architectonic alignments, we can compute the mean Hausdorff distance between the architectonic and parcellation boundaries. So lower distance means that the parcellation boundaries is closer to it aligns better with the architectonic boundaries. So this plot shows the architectonic alignment of Schaefer and Gordon parcellation, and we can see that the Schaefer parcellation achieves slightly better architectonic alignment. To evaluate connectivity, we can use the resonance state functional MRI data. The resonance state functional MRI data normally it should be from the out of sample test. So for example, if you use the data set A to estimate your parcellation, you're supposed to test the connectivity in out of sample test. Okay, so as the voxel level analysis is normally computationally very expensive. Therefore, the area level parcellation is normally utilized to define the region of interest for dimensionality reduction. Therefore, we will expect the time courses within a parcel to be very similar. So we have this metric called homogeneity. So the homogeneity can be can be defined as the so if we perform the PCA analysis on the functional connectivity patterns within a parcel, so this homogeneity is defined as the percent of total variance across all the vertices connectivity patterns that can be explained by the first principal component. So higher homogeneity means that the functional connectivity patterns of all the vertices within a parcel can be better described by a single connectivity pattern. Therefore, the higher value, the better the parcellation quality. So in this plot, the red dots represents the homogeneity of Gordon's parcellation. The black dots represents the non-model where the Gordon parcellation is randomly rotated like around 1,000 times. So there are possibly 1,000 black dots here. So this is important because in this non-model, in this randomly rotation non-model, the parcel location is relocated, but the relative position of parcels to each other are actually preserved. So in this way, we can see that the Gordon parcellation is significantly higher than the non-model. So this non-model is very useful here is because, as we know, the different parcellation could have different number of parcels. Therefore, it makes sense for like a parcellation with small parcels to have higher like homogeneity. Therefore, you have to look at the non-model to see like whether your parcellation, how much you can improve compared with the non-model by using your parcellation. There is another way to compute the homogeneity is by correlating the time courses within each parcel or network. So higher homogeneity means that the time courses within a parcel is more similar. So this bar chart shows the homogeneity of Schaefer and Glasser parcellation, and it's worth to mention that the number of parcels are matched here, else it's not comparable. To evaluate topography, we can look at the areas that has the internal topography. So for example, the visual areas from the isotopic mapping. So this figure shows the glasses parcellation overlaid with the isotopic areas. We can see that the alignment is very good. Therefore, we can align the parcellation boundaries on top of the isotopic boundaries to assess the parcellation quality. So similar to the architectonic alignment, we can again compute the mean Hausdorff distance between the isotopic and parcellation boundaries. So lower distance means that the parcellation boundaries aligns better with the isotopic areas. So this figure shows the superior isotopic alignment of glasses parcellation. So in summary, in this education course, I have described several approaches for estimating the network level parcellations, and it was to mention that although there are different approaches, but the large-scale networks are actually consistent across studies. I also described several area-level parcellation approaches, and because the area-level parcellation is normally utilized as the region of interest for dimensionality reduction, therefore, we would expect the time courses within each parcel to be highly similar. I also emphasize the importance of estimating the individual specific parcellations because apparently the group level parcellations obscure a lot of individual specific features that are actually behaviorally meaningful. And finally, you can use facts to quantify the parcellation quality. I would like to thank our lab members and our funding support. So, thank you. I actually have the questions. So, for questions, you can visit this website, participate. There are 3 questions, and it shouldn't be very hard.
We have 3 minutes for questions. So we also have 10 minutes question discussion at the end of the session, so we can also discuss this question at the end of the session, just to stay in the chat. Yeah?
Yeah, sure.
Thank you very much.
Okay, thank you.
Very, very nice.